Hello. Today we are gonna be doing some discrete math um, ASMR kind of. I'm gonna be trying to do some problems from my book, and yeah, I've already solved a little bit, but I would like to continue solving them because I have an exam in, or not an exam, like a quiz tomorrow. So I'd like to make sure that I am well prepared for that. So, how do I prepare myself? Well, luckily for me, I have access to the book, and the book has a lot of questions essentially, and I'm gonna be solving them, or at least trying to solve them. Not sure if I'm gonna be fully, capable, but that's perfect because if I don't understand, then I can learn from it. But if I do understand, then I can explain it to you, folks, and see how that works. So, I've started a little bit on chapter 7.1. We have the exam from 7.1 to 7.5. I'm almost done with the 7.1 questions. I'm going to move on to 2 and 3 and 4 and 5. Hopefully, I should be able to finish that under 2 hours. And yeah, because I want to go to sleep at 12. So, it's currently 10 o'clock, 10:18. Starting with this question, it says how many edges are in K of 3, 4? So K of 3, 4, it has 3. So I believe it goes by the edges and the vertices. So there are 3 edges per vertex, and there are 4 vertexes. So if that's the case, I would say there is, to find the edges, it's simply going to be multiplying each other, which is 12. 12 edges. And, is it a regular graph? Regular graph. It needs to have the same, yes, I believe, because they all have an edge of 3, they are a regular graph. Yes. And the answer is yes. So we can multiply 3 times 4 to get 12, which is correct. And yes, it's perfect because K 3, 4 is simply stating that there is a graph K that has edges 3, 4. So every vertex has an edge of 3. And how many vertexes do we have? We have 4. So we multiply the edges times the vertex, which gives us 12. And the graph is not regular because the vertices in A have a degree 4, and the vertices in B have a degree 3. Call the set with 3 vertices A and the set with 4 vertices. There are no edges in here, therefore there are 3 times 4, which is 12 edges in a graph. Vertex A, that's, okay, maybe I'm comprehending this incorrectly. In K3, 4, the vertices are divided into 2 sets. A set with 3 vertices and a set, oh, so if it's saying K3, 4, there are 2 graphs that have a set vertices of 3 and a set vertices of 4. Call the set with 3 vertices A and the set with 4 vertices B. There is an edge between each vertex in A and each vertex in B. There are no edges in the graph, therefore, the minimum, assuming the minimum amount of edges is 12 because you're multiplying the 2 vertices together. Because remember, I believe the number of edges is No, that's for the total degree. Never mind. Total degree is multiplying the number of edges times 2, which gives us the total degree. But in this case, it is going to be multiplying 2 vertices to give us the edge. It is not regular because the vertices in A, which is K3, has a degree of 4. Has a degree 4. Has a degree 4. And the vertices in B have a degree 3. I don't understand that. The graph is not regular because the vertices in A have a degree 4 and the vertices in B have a degree 3. Okay, so I don't understand that, so I'm gonna highlight that or star it, make sure to go over it again, and then let's move on. So question B says, how many edges are in K of 5? Is K of 5 a regular graph? Well, I believe each vertices should have at least one connection, right? At least one edge. So I believe there is I think at the same time I believe that it could be a different, because I remember making an object that was K to 5, which had a very specific degree. So I think saying that there's 5 edges is incorrect, and there probably is a formula, but I'm just gonna say 5 edges for now, just in case. Is K5 a regular graph? Sure. Let's see yes. My reasoning is because it is a single graph, and if it has a degree or a vertex of 5, then they should be connected to each other, which means that if they're connected to each other, they must have an equal amount of edges. So, what's the answer? There is an edge for every pair of vertices, so there are 5, 2, 10 edges. They say it's like a parentheses, and there 5 is on the top and 2 is on the bottom. There's no division symbol, and apparently that equals 10. So 5 times 2 is 10. So each vertex has 2 edges. There's an edge for every pair of vertices. So there are 5 vertices, which means that there are 10 edges in total. So if we have 5 vertices, we're just gonna multiply by 2. Got it. So this is wrong. The graph is a regular graph because every vertex has an edge to the 4 other vertices in the graph. So the degree of every vertex is 4. And degree is simply the number of connections. So yeah, I did believe, yeah, so it makes sense. So yeah, I had a feeling that if there was a single vertex for a graph, then it would most likely be a regular graph. Okay, I'm gonna put a star on this one too, just in case, because I would like to go over it again. Okay, C says, what is the largest n such that k of n is equal to c of n? Okay. What is the largest n such as k of n is equal to c of n? Okay, I don't understand this either. Which means I'm gonna have to go over it again. It's good. From what I understand, I believe it could. I think it could be infinity. Like, there doesn't necessarily seem to be a limit. K of 3 is equal to c of 2. Okay, that is wrong. Apparently, the limit is 3. So k of 3 is equal to c of 3. That's the largest n that is possible. Okay. Going to D, it states, for what value of n is q2 equal to c of n? Well, if that's the case, wouldn't that just be 2? Yeah, I seriously need to review over this. It seems like I do not understand, or maybe I just forgot, a couple of things from chapter 1. For what value of n is equal to c? Solution is q2 is equal to c4. Okay. Interesting. And then the final question is for this section, or this specific part in the section. Is q of n a regular graph where n is greater than 1, greater than or equal to 1? Is that greater than or equal to 1? If so, what is the degree of the vertices in q of n? I can't think of it on the top of my head. It states that every vertex in Qn has n neighbors, and Q of n is n regular. So it is n regular. If so, what is the degree of the vertices? The degree of the vertices is the n neighbors, which is essentially the degrees of the vertices are also n. Okay, so I'm going to go over that one as well. So, it looks like there's a chunk of problems that I simply did not understand. So I'm going to try to go back and redo them, because I would like to make sure that I'm actually understanding the problems. So, let's do it. Okay. Graph may appear to be disconnected into more than one piece, but is still considered one graph. It is also possible for a graph to have no edges at all. The diagram below shows two graphs whose vertices are blah 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 blah. Okay, that makes sense. So it's possible for a graph to have disconnected pieces, and it's also possible for the graph to have multiple vertices, so different points, but no connections, so no edges at all. Okay. So going back into the first question, this 7.1.1 states, match the graph drawing with the corresponding edge set. Oh, this is very nice, because from what I'm seeing, the specific problem is, so there are different sections in every section, and this section is specifically dealing with 7.1.1, and there is an additional exercise that is exactly 7.1.1, which means that if I get these right, then I should be good with 7.1.1 as well. So the question says, use 3 graphs below, all of which have a vertex set V is equal to A, B, C, D. A is equal to this, B is equal to that, so there's 3 different graphs. Match each edge set to the corresponding picture of the graph. So there's 3 of them. The edge set is fairly simple. A to B, B to C, and then B to D. So I can see that going with A. That's incorrect, okay. A to B, B to C, C to... Oh, okay, that's C actually. And then So the edge set is simply the number of edges that are in the graph, the number of connections that are in the graph. And they're giving us three different options that needs to be matched with the graph. So I found C. Now I need to find A and B. A, B, B, C, C, D, and then B, D. Okay, so that's A. And then the other ones, yeah. Fairly simple. Parallel edges, self loops, I understand that. Graph terminology. Yep, adjacent endpoints. Incident to vertices. Okay, that makes sense. Total degree is the sum of the degrees of all vertices. Degrees is the number of neighbors it has. So, for instance, B has a neighbor of 3 because it has 3 different connections. So the number of edges is simply the number of degrees, I believe. Yeah, so the number of neighbors it has is the number of degrees. So the total degree for such a graph is adding all the degrees that each vertex has, hence the total degree, which makes sense. In a regular graph, all vertices have the same degree. In a deregular graph, all vertices have degree d. So essentially, in a regular graph, in a regular graph, these vertices have what is it? So the vertices have the exact same degrees, and in a deregular graph, the vertices have the exact same degrees d. So whatever d is. So if d is 5, every single vertex has at least 5 neighbors. Okay, now they're talking about subgraphs. So subgraphs are essentially, let's see, so graph H is equal to V of H and E of H. Okay. Vertex of H and the edge of H is a subgraph of a graph G, which is the vertex of G and the edge of G. If the vertex of H is if the vertex of H is a improper subset of the vertex of G, and the edges of H is an improper subset of the edges of G, then it is a subgraph. Got it. So H is a subgraph of G because it has the number of edges, and it has the same number of connections inside, like same number of exact connections inside of G. It's a little bit hard to explain it just by talking, but it does make sense. I see how that makes sense. So, alright, 7.1.2. Where's the questions for 7.1.2? 1.1, 2, 3, 4. Okay, so let's start with the questions here. Is vertex C adjacent to vertex E? Well, it is not adjacent to vertex E because it is not a neighbor. They're not neighbors. They need to be neighbors. What is the degree of vertex D? Well, it's 3 because it has 3 neighbors. Is the graph a regular graph? No, because they don't have the exact number of degrees. Is it correct to say that the vertices D and E are incident? Incident implying that the vertices D and E have the same edge set, or you could connect and make it into an edge set. I'd say yes, it is. Okay, it is not. Two vertices. Oh, okay. Two vertices cannot be an incident to each other, but an edge set can be incident to one of the vertices. What is the total degree of the graph? Total degree of the graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it's 12. I just counted just by a simple check. Yep, it's 12. Is the following graph a subgraph of the graph above? So the changed V is BCE, and the edges is B to C. Wait, BCE, BCE, and then it's connecting, the edges are BC and a B. Yes, I do believe that's a sub, yeah, that looks like a subgraph, yeah. Perfect. So I got one wrong, which is, it's pretty good. So now I know that an edge is incident to a vertex, but two vertices cannot be incident to each other. Okay. So 7.1.1, there's a theorem. It states that the number of edges, essentially calculating the number of edges and total degree. It's saying that we're letting G is equal to V of E be an undirected graph, then twice the number of edges is equal to the total degree. So what it's saying is that the number of twice the number of edges. Okay. So the total degree is simply multiplying the edges by 2, right? So multiplying, so if we have an edge of 4, right? If there's an edge of 4, we multiply that by 2, we get a total degree of 8. Yeah, I think that makes sense. Okay, so they're doing the proof by induction. We don't necessarily need to worry about the proof, but it's nice to see. Okay, so there's some questions about the induction. What is the sum of degrees of the vertices in the graph depicted below? Sum of degrees in the graph depicted below. So sum of degrees 1, 2, 3, 4, 5. Well, wait, what am I saying? There is 1, 2, 3, 4, 5, 6, 7. So there's 7 edges, which means if I multiply by 2, we should get 14. Perfect. So there's 14 edges. Which of the following statements describes the inductive step and it proves the theorem by graph by induction on the number of vertices? So the theorem holds the graph. This one we don't really need to worry about. I don't think that's gonna be the quiz. I highly doubt it. Okay. So we're gonna move on to 7.1.5, which is another question set. Consider the set of classes and the corresponding times. Class A has Monday, Wednesday, Friday at 3 p.m. to 5 p.m. Class B has Wednesday from 2 p.m. to 4 p.m. Class C has Friday from 4:30 to 5:30 p.m. And Class D has Monday, Wednesday, Friday from 2:30 p.m. to 3:30 p.m. Okay. Which two classes conflict if meeting times overlap? Okay, so that would be either Class B and D, I believe. Yeah. So Wednesday, Class B and D overlaps. So which of the following graphs correspond to the constraints? So Class B and D should be overlapping. Okay, that makes sense. And then A and C. Yeah, their Monday and Fridays are conflicting as well. So it should be, it looks like it's is connected to C. Right after D, which is 3:30 p.m., we go to C, which is no, that shouldn't be right. So I think it is the last one. Yep. Okay. Perfect. Because when they're connected without intersecting, that means they go afterwards, right? So A is connected to B, implying that their 3 p.m. to 5 p.m. schedule aligns properly. However, yeah, so their Monday, so from A to B, their Monday schedule and their Friday schedule aligns properly, but their Wednesday schedule does not. Or maybe, okay, maybe I'm wrong. Maybe the number of edges is the number of constraints that the classes has. So from A to B, there is an issue with that. So that's why there's an edge there. From A to D, there should be an issue. Yes, there is an issue with that. So they, have an edge for that. From B to D, is there an issue? Yes, there is an issue. So they're crossing that off as well. And then from A to C, there is also an issue from A to C. So that's why they have another edge connection. That makes sense. Makes a lot of sense. Okay, so common graphs. Some graphs with special structures are given their own name and notation because they come up frequently in graph theory. The figure below shows some common examples. Okay, interesting. So K of n is called a complete graph on n vertices. K of n is called a complete graph. If I go back to my oh, did we just stop on 7.5? Yes, so we stop on 7.5. Yeah, so we're gonna have the quiz from 7.1 to 7.5, and yeah, so I think we should be good with that. Okay, so K of n is called the complete graph on n vertices. K of n has an edge between every pair of vertices. So the figure K of 6, the figure shows K of 6. K of n is sometimes called a clique of size n or n clique. C of n is called the cycle on n vertices. The edges connect the vertices in a ring. The picture above depicts C of 7. Note that C of n is well defined only for n is greater than or equal to 3. Okay? K of n is complete graph. C of n is a cycle graph. Is a cycle on n vertices. So, okay, and K of nm is stating that it has n plus m vertices. The vertices are divided into two sets, one with m vertices and one with n vertices. There are no edges between vertices in the same set, but there is an edge between every vertex in one set and every vertex in the other set. The figure shows a diagram of K34. Okay, and that makes sense. So K34 is essentially, there's 3 vertices in one graph, or there's 3 vertices in that one graph, and there's 4 in the other graph. And those 3 vertices do not connect with each other, but they do connect with the 4 vertices in the other, part. So the vertex, so they're essentially connected in that way. Which means that, how do we count the edges? We multiply 3 times 4 to find the amount of edges that there is. And if we want to find the total degree of that, we can simply multiply that by 2 to find the total degree. In this case, if it's graph 3, 4, then the total degree should be 24, because 3 times 4 is 12, which is the edges, and 12 times 2 is 24, which is the total degree. So there's another question set. So we're just doing some simple notation. So I can immediately see 3 of 2, which is for C, D, which is a cycle of 5. 1, 2, 3, 4. Oh, whoops, that is B. Cycle of 6 is D, and then K of 5 is simply a complete graph, which means that they have the exact same degrees. There's an edge between every, K of n is an edge between every pair of vertices. So if there's a K of 5, then that means every single one of them has a connection of 4. That means there are four neighbors for every single one of them, which implies that to find the number of edges in a complete graph, you're subtracting the n minus 1, which gives us the number of edges in one vertex. So if there's 4 edges in one vertex and there's 5 of them in total, then that means the total edges is 20, because you're multiplying the number of vertices, which is 5, times the number of edges, which is 4, gives us 20. Total degree is 40. Okay. Because the K of 6 has 1, 2, 3, 4. Yeah, K of 6 is it's also a complete graph, and it has 5 edges connecting to each other, which makes sense. So let's go back and whoops. Okay, I'm just gonna refresh the page. Hopefully, if I refresh the page, it will give me. Oh yeah. Okay, it will give me the. Okay, good. So it'll cover up the solutions. Now, if we do it again, which we are gonna do again, I should be much better. So, so 7.1.1, question A. Okay, so what is the total degree of G? Total degree of G is simply the number of edges, which is 1, 2, 3, 4, 5, 6, 7, multiplied by 2, which is 12. 12 should be the total degree of G. Wait, 14 I mean. Why did I do 12? My multiplication is a little bit off. Oopsies. Okay, so that should be 14. List the neighbors of vertex 5. They're neighbors of vertex 5. So the neighbors of vertex 5 is 1, 2, 3, 4, and 6. Is that correct? Perfect. Okay. What is the degree of vertex 6? The degree of vertex 6 is 1. Yep. Because it only has one neighbor. Which vertices are adjacent to vertex 3? Let's see. 2 and 5. 2 and 5 are adjacent to vertex 3. Yep, perfect. Is G a regular graph? Why or why not? Well, what is a regular graph? Regular graph means that the number of degrees that each vertex has to be the same. So, if that's the case, then no, it's not. Because vertex 6, for instance, has a degree of 1, while vertex 5, for instance, has a degree of 5. So, no, they're not the same. Is K of 3 a subgraph of G? If so, name the vertices in the subgraph. So remember, K of 3 is simply stating that um, K of 3 is simply stating that there is 3 vertices that has 2 edges each. Let me just write that down. So K of 3 is equal to 3 vertices that each have 2 edges. And if we were to look at the graph, there is 3 vertices here, and so this one has, okay, so vertices 1, 2, and 5 is one of them, and vertices 2, 3, and 5 is the other. So vertices 2, 3, 5, and vertices 1, 2, and 5. Perfect. Is K of 4 a subgraph of G? If so, name the vertices in the subgraph. Well, let's see. K of 4 implies that there are 4 vertices that have 3 edges each. And immediately looking at the graph, there's none. Perfect. Okay. 7.1.2 is okay. It's almost like proving a theorem, so I'm gonna skip that. I don't think that's gonna be on the quiz. So, 7.1.3. Is it possible to have a 3 regular graph, meaning that there is a vertex of 3? Or, no, 3 regular graphs states that the number of degrees is 3 for every vertex, which is implying that there is 3 edges for every vertex. If such a graph is possible, draw an example. If such a graph is not possible, explain why not. Okay, so is it possible for a 3 regular graph to have 5 vertices? 3 regular graph, which means that each vertices has a degree of 3. So if we multiply 3 times 5, if we multiply 3 times 5, that's going to give us 15. And 15 is the total degree, or total is the complete number of edges. Now, you can't have an odd number of edges because in order to find the total edge, you need to multiply 2 times the number of edges. But in this case, it's odd. So you can't ever have an odd edge. So I will say no, because 3 times 5 is equal to 15 edges, and you cannot have an odd number of edges, of total edges. No, it's not possible. The total degree cannot be odd. Okay. Or same thing, essentially. Is it possible to have a 3 regular graph with 6 vertices? Immediately I can see that yes, it is possible, because you're multiplying 3 times 6, which is 18. If such a graph is possible, draw an example. If such a graph is not. Yes, it is possible. 3 regular graph with 6 vertices. Okay, so if I draw on 6 points, I've already seen this before, so it's easy for me to do it. But yeah, so that's how you would do a three-regular graph, which would essentially be this: three different vertices or six different vertices, 1, 2, 3, 4, 5, 6, and then each of them has three edges. Okay. And then we're back to 7.1.4, so we're in a full loop. So we're going a little bit slower than expected, but that's okay because the most important thing is to understand. I'd rather understand. I'd rather fully understand like 4 sections out of the 5 rather than vaguely understand 5 sections. So, how many edges are in K of 3, 4? So K of 3, 4 is stating that there's 2 of them, 2 sets of 3 vertices, and then so if there's a vertex of 3 and if there's a vertex of 4, then you're simply saying that there's 2 edges with a 3, right? 2 edges with 3 vertices. So for A, it's going to be 2 times 3 plus 3 times 4. So 12 plus 6, which is equal to 18 edges in total. And is K of 3 to 4 a regular graph? No, because the degrees are not the same. So the degree of K of 3 is 2, and K of 4 is 3. Let's see. Oh, okay. I see. So I forgot. So when there's a problem such as K of 3 or 4, so if there's 2 different vertices, so like K of 3, 4, 3 comma 4, you multiply the vertices to get the total number of edges. So I'm going to erase this. 3 times 4 is equal to 12 edges. Okay, at least I got the non-regular graph, because it is not a regular graph because the vertices in A have a degree 4 and the vertices in B have a degree 3. And if I were, is that true? One, two, one, two, one, two. Yes. Okay, I think that's what it's supposed to look like. Vertices in A have a degree 4. That doesn't make sense to me though. Yeah, that. K of 3, 4. it does make sense. It makes sense because once you graph it out, you will see that, yes, A has 4 degrees and B has 3 degrees. Okay, so that makes sense. How many edges are in K of 5? Is K of 5 a regular graph? So K of 5, so there's 5 vertices and each vertices has 4. So K of 5, so B, K of 5 is equal to 5 times 4, which is equal to 20 edges. And is K of 5 a regular graph? Yes. Oh my god. There's an edge for every pair of vertices. So there are 5 times 2 edges in K of 5. There's 10 edges in K of 5. How does that make any sense? It's not a C of 5. It's a K of 5. There's an edge for every pair of vertices. I want to see this K of 5. Okay, so K of 5 is A, right? Yeah. Oh my god, it does have 10. What the heck? That's how edges are different from degrees, because edges simply state how many connections there are. So there are 1, 2, 3, 4, 5. There are 10 connections, but each vertex can have multiple neighbors, multiple connections. So that's how degrees are different from edges. Okay, that makes a lot of sense. That makes a lot of sense. Okay. So you just multiply 5 times 2. Or you could just graph it too, honestly. You could graph it to be completely sure, but yeah, it's gonna be 10 edges. There's a pair, which is there's two edges for every vertex, which means 5 times 2 is 10. What is the largest n such that K of n is equal to C of n? Well, let's think for a second. K of n is the number of complete graphs, right? The number of vertices in a complete graph. If it's 5, I don't get it. K of 3 is equal to 3 because where K of n is not equal to the C of n for K of 3 is equal to C of 3, which is stating that the number of vertices in 3, K of 3 is equal to the number of vertices in C, which means that there's 3 times 6. The degree of every vertex in C of n is equal to 2. But the degree of every vertex in K of n is equal to n minus 1. Okay. So C n has to equal to 3 because when K of n is equal to 4, you subtract 1 is equal to 3, which gives you the number of degrees for every vertex. Interesting. For what value of n is q of 2 is equal to c of n? So q of 2 is equal to c of n. So we know like c of n is the number of cycles of n. Q of 2, I don't know. I don't know why. So Q of 2 is a regular graph, which means that there's two vertices. There's two vertices in Q, which has one edge each. I'm a little bit confused. Q of 3 is a three-dimensional square. The n-dimensional hypercube denoted Q of n has 2 to the n vertices. Ah, 2 to the n vertices. Each vertex is labeled with n bit string. Q to the n is 2 to the n. Okay, so for D, Q to the n is, or Q to the 2 is basically is equal to 2 to the power 2, which is equal to 4 edges. No, 4 vertices. Got it. Q of n is a regular graph where n is equal to greater than 1. If so, what is the degree of vertices in Q? It's just going to be n. Okay, so E is n comma n. Alright, I think we're good with 7.1. That took 40 minutes for 7.1. That was very long for 7.1. But luckily 7.2 is a little bit shorter, I think. Okay, so let's do this. Seven point 2.1. And I hope that you should be, asleep by now from all this talking. But if not, then continue along. We will do 7.2. So it doesn't seem to be as much as 7.1, but who knows? We'll see. So question A states, draw the graph based on its representation. V is equal to ABCD and E is equal to that. Like, so they're giving us the vertices and they're giving us the edges. So there's 4 vertices, so 1, 2, 3, 4. So I'm basically gonna put a square because of the number of vertices. There's connection between A and B. So I'm gonna put A is right here. So there's an A is connected to B, but it's also connected to D. So let's say that this is B and D is right here. So it's connected to D. B is connected to C. Okay. B is connected to D. And C is connected to D. So it looks like a so they got something different, but I got this, which technically does make sense. Wait a second, why did I write that? Oh no. That's why. So if I flip to the orientation, ABCD. A is connected to B, A is connected to D, B is connected to C, B is connected to D, C is connected to D. That makes a lot more sense. So they're going like step by step by step by step by step. Okay. Let's go to B. Oh, okay. So we're gonna have to draw another graph. So A connected to BD. Oh, that's pretty cool. Okay, so A, 1, 2, 3, 4, 5. So there's 1, 2, 3, 4, 5. So A is connected to BD. So if we put A right here, and then we put D right here. B is connected to C, AC, and E. Okay. So B is connected to A, C, okay. I'm starting to see the shape. So B is connected to A, B is also connected to C, and B is also connected to E. C is connected to B and D. Okay, I can see that. D is connected to AC and E. And finally, E is connected to B and D. Which makes sense. So I ended up getting like something like this. Let's see if they got the same. Not bad. It looks essentially the same. Yeah. Okay, so now they have a matrix. Matrix. That's gonna be fun. So there's 1, 2, it's a 5 by 5 graph. So we do know that there is 5 vertices. Okay. I'm gonna draw the same one again. So 1, 2, 3, 4, 5. So let's say that's A, B, C, D, E, right? So A is connected to A is not connected to A is connected to B. So A is connected to B, A is connected to C, and then it's not connected to that. Now B is connected to E. C is connected to itself. C is what? No, C is connected to A. Whoops. C is connected to A. That makes sense. C is also connected to D and E. So this is D, boom, and boom. D is connected to C. That makes sense. And it is also connected to E. That makes sense. And finally, E is connected to B, C, and D. There we go. So we got like a something like that. And the answer is, there we go. It was very similar. All right, so I've mastered the art of 7.2.1. I'm very happy about that. Let's do 7.2.2, which is sample 2.2, and then there's A graph G is depicted in the diagram below. 1, 2, 3, 4, 5. Give the adjacency list representation of G. Oh my god, it wants me to give the entire adjacency list? Okay, I'm gonna say that it's gonna be the entire adjacency. So like 1 to 2, 2 to 3. So like 1 to 2, 1 to 5, 2 to 1, 2 to 3, 2 to 5, things like that. Let's see. Oh, okay. So adjacency is simply like making the column of boxes and like connecting them. So okay, so it's not a set, it's an adjacency. So 1, 2, 3, 4, 5, 6. Okay, I'm not gonna copy it perfectly. And then it's telling me that, pointing an arrow, boop, 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 boop. And then 1 is connected to 2 and 5. It's a very nice way of doing these things. Two is connected to 1, 3, and 5. So 1, 3, 5. 3 is connected to 2 and 5. 4 is connected to 5. 5 is connected to, holy, okay, so 5 is connected to 1, 2, 1, 2, 3, 4, and 6. And 6 is connected to 5. Perfect. And now question B is asking us to give us the matrix representation of G. That's going to be very simple as well. So there's 6, so it's going to be a 6 by 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 1. So then it's a simple 6 by 6. Oops, that was pretty bad. Trying to draw a fairly nice line. Okay, so 1 is connected to, so let me just draw a 0 on the diagonal because it does not have a self loop. So it's connected to 2, right? So 2 and 5. The rest are zeros. 2 is connected to 1, 3, and 5. The rest are zeros. 3 is connected to 2 and 5. The rest are zeros. 4 is connected to 5. The rest are zeros. 5 is connected to everything. 6 is connected to 5. There we go. Easy as that. Nice. Let's go. So it seems to me that I'm very, very good at doing 7.2 so far, but I don't want to overestimate myself. I might get stuck in the future. 7.2.3. I'm starting to lose my voice. Maybe I should, I don't know. I tend to lose my voice when I'm talking a lot. But it seems to me that I'm losing my voice a lot faster than other people. I don't know. So, indicate if two graphs are equal. So saying for A, there's two graphs. Let's see. They need to have the same number of edges. So 1, 2, 3, 1, 2, 3. Okay, they have the same number of edges. Do they have the same number of degrees? 2, 2, 1, 2, 2, 1. Yes. Therefore, I think it is. Yes, I think they are equal. So yes, A is equal. Yep. There we go. B. Well, let's see. So, oh, that's interesting. So they're giving us a graph and they're giving us an adjacency list. So for the graph, they have 1, 2, 3, 4, 5, 6. Right. Okay. 1, 2, 3, 4, 5, 6. The adjacency list is kind of annoying because I need to figure out like exactly how much there are. But I think if I can find out the total degree, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6 times 2 is 12. Right? 12. 4, 5, 6, 7, 8, 12. Okay, they have the same number of degrees as well. So just based on that, I would say yes, they are Yep, they're the same. Yep. They have the same number of vertices. They have the same number of. Wait. Both representations correspond to the graph with vert A, B, C, D, E, and the edge set A, B. So A is connected to B and also connected to C. B is connected to A. Oh wait, that's even easier. That's way easier. So all we have to do if the two graphs are the same is we just check if the edge set and the vertices are the same. So for instance, for A, the edge set needs to be so AC, BD, CD needs to be the same as the other one. Yeah, and it is. Wow, that's really easy actually. So in order to see if two graphs are the same, just check the edge sets. Okay, so I was gonna write this down. In order to check if two graphs have the same edge set, if two other graphs have the same edge set, and number of vertices, then they are they are the same. It seems to me as if my sleep is starting to catch up. Because around 12 o'clock I do need to go to sleep because I need to wake up at approximately 7 to 8 p.m. or 8 a.m. I need to wake up at that time so that I can be ready to go to my class. Thank goodness I don't have my 9 a.m. class because I don't know, it's like they canceled essentially. But I do have my 10 a.m., which is my exam or my quiz. So we'll see what happens. C is what? Okay, so oh wow. Okay. So C is simply so now it's comparing a graph to a matrix. So A is connected to C and D. Okay, that makes sense. B is connected to E. Okay, that makes sense. C is connected to A and B. C is connected to A and D. Oh, never mind, A and D. Okay, that makes sense. D is connected to A, C, and E. Ooh, caught him there. So C is not the same graph. Exactly. The last one for this question is A, B, C, D, E, A, C, A, D, B, D, B, E, E, D, or D, and C, D. It looks, wait. It looks good. It looks like they're the same. Yes. There we go. And then finally the last section for chapter, or section 7.2. Given a vertex I, list all the neighbors of vertex I. What? Okay, I don't think we need to do these. For D's, go to D. about this being on the quiz. I highly doubt. So I'm gonna skip that. Okay, so 7.2 was a lot faster, which is very nice. It seems as though I have essentially mastered 7.2. Or, yeah, not 7.5, 7.2. Okay, so 7.3.1 is 7.3 seems to be a little bit simple as well. Let's see. We're not entirely sure, but let's see. Okay. If I can finish 7.3 for today, when I wake up tomorrow morning, I'll have 2 hours to not only get my breakfast, wash my face and everything, but I'll also have to, I'll have like basically 1 hour to review over 7.4 and 7.5, which shouldn't be too bad. Like the most important thing is sleep. Like sleep is literally one of the most important things. So I'd rather sleep and I can have a logical mindset than, you know, try to wake up and, or like not have enough sleep and just like kind of like just, you know, fail the exam or quiz or not do as well. Okay, moving on. The question is asking, prove that the two graphs below are isomorphic. So, are they isomorphic? Let's see. Ooh, crap. I kind of forgot what isomorphic is. Oh, okay. I think to prove if two graphs are isomorphic or not, we need to see if they have the same number of degrees. Like each individual degree needs to be equal to the other ones. So for instance, I see that A has 1, 2, 3, 4, 5 degrees. 5 has 1, 2, 3, 4, 5. So we can estimate that A and 5 are matching. What about for D? D has 1, 2. So we can estimate that 6 is connected to D. What about B? B is connected to 3 different ones, right? 1, 2, 3. We could assume that B is connected to 3. What about C? C is 1, 2. So we could connect C with 4. And finally, or not finally, we have E, which has 1, 2. We can connect E with number 1. Something. And then finally, F has 1, 2, 3, 4. And we can connect F with 2. So yes, they are isomorphic. Exactly. That was exactly the perfect solution. Okay, so I do remember. Okay, so it seems as though I remember what isomorphism is, which is very nice. Well, that's the reward of going to class every single day. So that's very nice. For each pair of graphs, show that they are not isomorphic by showing that there's a property that's preserved under isomorphism, for which one graph has and the other does not. Okay, so Well, it's not isomorphic because 5 has a degree of 2, while E has a degree of 3. Degree of 2. The degree is equal to 3. They are not isomorphic. Okay, so I need to understand the rules of isomorphism. It states that the number of edges needs to be the same, right? The graph on the left has an edge of 7, total edge of 7. The graph on the right has a total edge of 8. So they are not isomorphic by that standard. Got it. Ooh, my hand's getting kind of stiff now. It's like losing its energy slowly. Okay, so B. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, edges are matching up. That's good. 1, 2, 3, 4. 1, 2, 5. But the vertices. No. Not because the vertices are not the same. Yep. And then the last one is 1, 2, 3, 4. 1, 2. Wait. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Same number of edges, same number of vertices. I'm assuming the total degrees are different. Wait, 3, 6, 9. 3, 6, 9. 12, 13. Okay, so the edges are not equal to each other. 2, 3, 4, 5, 6. Oh no, the edges are the same. But there is, so edges are the same, but the graph on the left has a so for C, the degree of vertex 1 is equal to 4, and the degree of A is equal to 3, or any other vertex is 3. So the graph on the left has the highest degree, which yeah, the graph on the right does not have a degree 4 vertex. It needs to have the same vertex. Let's move on to draw all non-isomorphic simple graphs with 3 vertices. Do not label the vertices of the graph. You should not include 2 graphs that are isomorphic. Remember that it is possible for a graph to appear to be disconnected into more than one piece, or to even have no edges at all. Draw all of them. Three vertices. Okay, I don't know. Oh, there's 4 different options. Okay, so that. Okay. What about that though? Does that not count? non-isomorphic. Oh, okay, okay. Wow, that's interesting. So, and then wow. Non-isomorphic essentially stating that if there are two graphs, they cannot be the same number of degrees, edges, same things like that. Interesting. Wow. That's a pretty cool question. And then for 4 vertices, if it's 2 to the power of 4 or 2 to the power of 3 to the power of, maybe it's the number of vertices plus 1. So if there is 4 vertices, then there should be 5 total non-isomorphic graphs, which means this is 1, this is 2, this is 3, this is 4, this is 5. Hey, okay, so that's a cool rule. So for non-isomorphic graphs, if to draw the total number of the non-isomorphic graphs, you just need to add 1 to the vertices. So there should be 5 total. And I lied. Okay, never mind. There's a lot more connections. But I don't necessarily. I'm just gonna put a triple dot. I don't think he's gonna quiz us on this specific pattern because it just takes too much time. It's a quiz. It's not supposed to be an exam, right? So 7.3.4 question A states, prove that for any k, the property of having C of k as a subgraph is preserved under isomorphism. Prove that for any k, the property of having C of k as a subgraph is preserved under C of k is the cycle of k. I don't think we need to worry about that. I'm gonna skip that. I really don't want to do, I hope he doesn't have proofs because it is such a massive amount of writing. Let G and G prime be two graphs and F an isomorphism from G to G. Suppose that G has C of k as a subgraph and there are vertices such that for I is equal to is an edge. The property is not. Yeah. It's for us to understand and memorize that entire paragraph of equations and words and whatnot. It's a bit much for a quiz. Besides, it's gonna be 20 minutes. Quiz is probably gonna be 15-20 minutes long, not the whole class. Use the fact from part A to show that the following two graphs are not isomorphic. Oh, okay. I'm gonna skip that too because if we're gonna be using the part from that, then we don't necessarily need that for the quiz. Alright. 7.1 seems to be the most confusing one, which I didn't understand until now. So, very good. 7.2, very nice. 7.3, very nice. So, I am good to go. going to be going to sleep soon. So I hope you enjoyed the video. I will be uploading this very shortly. And yeah, have a good night.